Hello everyone. So today's problem is flow over a circular cylinder, and we need to solve this problem using ANSYS CFX. So the problem states that there is a cylinder of diameter 0.02 millimeter and it is surrounded by a rectangle domain where this is inlet, this is outlet, and these green two lines are the top and bottom surface. So from inlet to the first point of the circle, the distance is L infinity, and from this point to the outlet, this distance is LO, and the values of L infinity and LO is given to you. Also, the height of the rectangle is given to you, which is 10 times B. So I'll show you step by step, starting from creating the geometry, then mesh, then setup, solution, and finally the result. So let's get started. So we'll start from ANSYS workbench. This is the new window, and we want to drag fluid flow CFX onto the project schematic. So for the given problem, these are the steps we need to follow to get the full results, where the first point is create the geometry in design modeler. So let's start with the creating geometry in design modeler. Because it says we need to create geometry in design modeler, so right click on geometry, then select new design modeler geometry. Okay, so we get the new window of design modeler. First step is to check the units, if it's in meter or not, because all the dimensions in the given problem is given in meters. Then let's select it to Z to make it 2D in XY plane. Select sketching, starting with settings. Click on grid and snap, and change it to 1 meter for major grid and minor grid. Then click on draw. Let's start with circle. So click on circle. When you move the cursor close to the origin, you should see P, and that time draw the circle. Let's draw a rectangle around the circle. Alright. Then click on dimensions. Let's start with the diameter of the circle. So I select diameter. In the problem, the diameter of the circle is given to 0.2 meter. So let's change this diameter to 0.2 meter and hit enter. Now zoom in here, and we should see the circle. Next, we want to select the dimensions of the rectangle domain around the circle. So let's first calculate from the given problem. So because this is a circle, so A and B will be equal, which is 0.2 millimeter. Then L infinity is given in the problem as 5A, so in our case it should be 1 meter. LO, which is given as 10A, this time it should be 2 meter, and H, which is given in the problem as 10 times B, so for our case it should be 2 meter. So let's create this domain for our case. Alright, so let's select horizontal dimension, and then select this circle 1 times, and then we are looking for one vertex of the rectangle. Once we get it, select this one. So this should be our L infinity, which is in our case 1 meter. So enter 1 meter and hit enter. Next, similar way, select the circle again, and looking for another vertex on right hand side. So, and this H3 should be 2 meter in our case. Now because the cylinder is vertically centered, so when we select the vertical dimension, we should select the center of the circle, and then let's click on the top vertex of the rectangle, and this should be 1 meter, which is half of h. Enter. And we also calculated that h for this case is 2 meters, so just click first top vertex and bottom vertex, and this should be 2 meters. Alright, so we created this geometry. Let's fit to this window, then click on modeling, expand XY plane. So this is our sketch. You can hide this dimension. Even though this is a 2D problem, but still CFX doesn't allow us to run 2D, so we want to make it quasi 2D model. So let's click on extrude. For the geometry, let's select the sketch one that we just created, hit apply. For direction vector, click XY plane. So we want the extrude should occur on Z direction. That's why we hit XY plane, apply, and the direction should be normal to the XY plane, so keep it as it is. So the thickness of the model, let's consider 3 mm, which would be 0.003, and then hit generate. So this is our model with the thickness of 3 mm. Once it's done, hit save, and that's how we create geometry for this problem. Once we created the geometry, next step would be creating the mesh. To create the mesh, right click on the mesh, hit edit, beside the mesh. So what we want to do, we want to just generate mesh to see how it looks like when it created automatically. So it looks like this. Alright, so let's right click on mesh, insert method, and then select the geometry, hit apply. From the method drop down menu, select tetrahedrons, and then update the mesh. So when you click on mesh, you should see final mesh has been created. Now select the edge. Let's select the circle edge and right click on it, insert, sizing. So edge has been selected. From drop down menu of type, we want to change it to number of divisions. Let's try with 200, and then again update or generate mesh, whatever. Click on mesh. Because we want to see velocity, lift and drag around this circular body, so that's why we want to make finer mesh around this circle, which we did. Next step would be to give the name of each surface of this geometry. So we make it as 3D. Let's click on face. We want to select any face, right click on it, then select create name selection. Let's start with bronze because this is bronze surface. Then zoom in to select this top surface. Right click on it, This is top wall, so let's click top wall. Using this fan, you can move the geometry and then select face. To select any face, right click on it. So this should be outlet, because in the problem we already see that inlet is closer to the circular body compared to the outlet, so this should be outlet. Then using your mouse, you can rotate this body to select other surface. This would be our bottom surface. Then this is the inlet surface. Inlet is okay. Then zoom in to select the circular face. Let's name it as circle wall. Last, we have to rotate this geometric to select back surface, and let's name it back. So if you expand this name selection, you should have seven names. So let's check whether we selected the right or not. So this is the front surface, this is the top wall, this is the outlet, this is bottom wall, inlet, circular wall, and this is back. So this is good. So that's how we created mesh, and that's how we name each phase of the geometry. Once we're happy with this, save the project. So our next step would be to set up the boundary conditions for this geometry. Once we save the project and close the mesh, if you see no tick sign here, just right click on the mesh and update. The project will update the mesh. Alright, so now we are ready to set up for our geometry. Alright, so our next step is setting up the boundary condition for the geometry. Before we start setup, let's review the boundary condition that has been given in the problem. So the green line representing no slip wall. Inlet is subsonic normal speed, and it should be constant inlet velocity, which is denoted as U infinity. Blue is the outline, it is atmospheric pressure, and the value is also given to you. The black line, which no slip wall, and front and back surface would be symmetric. The fluid flowing through the channel is water at 10 degrees Celsius. Density and dynamic viscosity is given to us. Inlet velocity is given as 30, 40, and 50 meters per second. Outlet pressure is given to us. Flow should be turbulent using default settings, so we don't need to change the settings for the turbulent flow. And the velocity at walls should be 0, that means no slip wall conditions. Okay, now we can double click on setup to start the setup for the boundary conditions. Alright, so first step is to insert all the boundary conditions and set the boundary condition according to the problem that we just reviewed a few minutes before. So let's insert boundary condition. Let's start with inlet. So write down inlet. Okay, so it automatically locate inlet, and then boundary details. It's already subsonic. It's also selected as normal speed, so we just need to enter here our speed. Let's start with 30 meters per second. then apply. Okay, then right click on it, insert boundary, this time to enter outlet. Okay, so again it automatically locate outlet. Now let's click on boundary details. This time the relative pressure, the pressure has been given to us, which is atmospheric, 101325 Pascal. Apply. Okay, right click on it, insert boundary, let's enter front surface. Now this time we need to change the boundary type, which will be symmetry, and then apply. Okay, similar way we can also insert for back surface. Okay, we need to change the boundary type to symmetry, apply. Okay, right click on default domain, insert boundary, this time let's select cylinder circle wall. Okay, again we need to change this cylinder circle wall to wall, and on boundary details it should be no slip wall, so it's there, no slip wall, so we just keep it as it is. Apply. Okay, right click on the default domain, boundary, this time we want to select top wall of the geometry. Again we want to change the boundary type to wall, and this is no slip wall that has been mentioned in the problem, so apply. Okay, similar way we can select bottom wall, boundary, no slip, apply. Okay, so we have all the 7 faces has been given the required boundary condition. Now double click on a default domain. The material, we need to change it because the material has been given to us as water, and then click on fluid models. The temperature should be 10 degrees Celsius. Now because alright, so if we want to check whether our flow is turbulent or laminar, let's consider Reynolds number equation, which is rho u infinity d by mu, where density of the flowing fluid water is given to us as 1000, inlet velocity is 30 meter per second, and the characteristics length here is 2 meter, and the dynamic viscosity is given to us 1.3 to the power minus 7. So if we calculate, we get 4 e to the power 7, which is definitely a turbulent model or turbulent flow. That means so our turbulence option, which is K epsilon, is one type of turbulent model. We want to keep it as it is because in the problem it says keep as default setting, so we don't want to change it. So hit apply. Okay, then expand the materials, double click on water, want to change the material properties, so hit on material properties, change the density, which is given to us as 1000 kg per meter cube. Then expand transport properties, dynamic viscosity is given to us at 1.307 e to the power minus 3, and also the unit is given to us as Pascal second, so we want to change it to Pascal second, and also the reference temperature we want to change it to 10 degrees Celsius. Once we are happy with this, hit apply. Okay. Next we want to insert 2 expressions, one for drag coefficient, the other is lift coefficient. So right click on expressions, insert, click on expression, let's name it as drag rho e. Okay, now here we can copy our expression which is given to us in the problem statement. So I just copied from the problem that is given the general equation. Drag is acting in x direction, so that's why we select force at x. Now at the body we want to change it. Select this, right click on it, select mesh locators 2D, and from here we want to see drag as circle wall, so select circle wall, and then again change this the body, delete this, right click on it, select exactly same way the circle wall, and also you want to change the inlet, so delete this inlet, right click on it, exactly same way, this time we want inlet. You might need to notice that here inlet is written as capital I, which CFX will select as error, so we want to select inlet what it is and then apply exactly same way. We can just copy this, then we want to insert lift coefficient, so insert expression, this time we write lift OE. Okay, paste this time all expression should be same except the force will be acting at y direction. Hit apply. Alright, now right click, now click on outline. We want to select the solver control right now, double click on it, minimum iteration, let's try the minimum iteration to 50, maximum iteration 100, and at the moment we don't want to change the residual target. Apply. Okay, save the project. Now we are ready to run the simulation. Alright, so now double click on solution. Now take double position, select the host name and start. The solution has been, the simulation started to run. Okay, the solution has been completed normally. Now what we want to see that how long does it take to run the simulation, which is 21 seconds. And if we just scroll up, then here you can see the pressure, velocity in x, y, z direction. So the pressure is, minimum pressure is negative 1.2 e to the power of 6 and maximum is this value. Once we are happy with the simulation, let's look at the results. So double click on the results. Okay, so the geometry has been loaded with the simulation results. Let's go back to the problem statement where we are asked to see several stuff. Let's check this first. Okay, so we are asked to calculate drag and lift coefficient for 30, 40 and 50 meter per second. We are also asked to find axial velocity profile in y direction for the given body, and at the prescribed lines we are asked to plot the velocity streamlines and pressure control line around the body. Start to see the results. Okay, first of all, let's see the pressure contour around the circular body. So to see that, click on volume rendering. Let's name it as pressure contour. Hit OK. Just apply, and that's it looks like. Okay, and see for the velocity contour, velocity magnitude contour, even though we are not asked to do that. So let's change it to pressure again. Alright, next just select streamline, hit OK, and then from the start from option, from the drop down menu, select inlet. So we want to see streamline from inlet, hit apply. Alright, so we can't see anything. What happens if we don't untick the pressure contour? We can't see that. So untick the pressure contour. Now we can see the streamlines. Because this is 25 number, so let's make it denser. So let's change it to 125 and then hit apply. Now we can see the streamline better. Alright, untick the streamline. Let's see lift and drag coefficient for these results. So click on expressions and then you should see drag coefficient, double click on it, so you get the result from here. So for this simulation we got drag coefficient as 0.0630186. let's click on lift coefficient, and for that lift coefficient we get 0.084665, which is really small. Alright, then we can click on location, select line, let's say it's point A, and hit OK. Now to get the coordinate of the point A, let's go back to our problem. Okay, so the problem statement, from the problem statement we see that line A is 0.5 meter away from the center of the circle. Line B is 0.5 meter away from the center of the circle. A is on the left, B is on the right. Line C is 1.5 A meter away from the center, and D is 5.5 A meter away from the center. So let's calculate the x coordinate. Y coordinate should be easy because this is 2 meter height and the body, circular body is at the center. So it should, if this is 1 meter, this should be -1 meter. So for all the lines, y coordinate should be 1 meter to -1 meter. So if we again consider the origin of the so if we consider the origin of the geometry, then the x coordinate range for point A should be -0.5A to -0.5A. Point B should be 0.5A to 0.5A. Point C should be 1.5A to 1.5A, and point D should be 5.5A to 5.5A. Let's plot all of these points. As we a little bit earlier calculated the x coordinate and y coordinate for point A, so it should be -0.1 to -0.1. Y coordinate should be 1 to -1, and we don't want to change the z direction. The color should be yellow, so we want to keep it like this. Hit apply, and this is our point A. Similar way, again select location, select line, this time let's name it as point B. Okay, so x coordinate of point B should be 0.1, 0.1, y coordinate should be 1 to -1, Let's change the color, maybe green. Okay, apply. So this is our point B. Point C. Okay, so point C is 1.5. Point C, x coordinate is 1.5a, which means 0.3 meter. 0.3 meter, and y coordinate should be the same range, from 1 to -1. Change the color, maroon. Okay, apply, and that is our point C. And let's plot the last point, which is point D. So point D, the x coordinate is 5.5 a, so it should be 1.1 meter. 1.1 meter. Y should be 1 to -1. Let's change the color of this line, maybe black. Okay, apply. So this is how we created 4 lines, point A, B, C, D. Next step, we want to plot velocity profile to all of these lines. To do that, click on chart. Let's name it as velocity profiles. Hit OK. In general, title could be velocity versus capital Y data series. Let's name it as point A, just to make it easy. Location, we want to start with point A line. X-axis, so this would be X-axis. So in X-axis, we want to select Y. That means this is Y. So we want to plot this length of the rectangle or rectangle domain, and in Y direction we want to see the velocity in Y direction. That means V, velocity V, and then apply. So this is length of the rectangle and this is velocity. Alright, let's click on data series, click on the new, and this time we want to C at point B. Location should be point B, and then apply. Next, I want to see at point C. Location is point C. Apply. Last is point D. Location is also point D, and hit apply. You can see from here point A, B, C, D, which is really easy to understand which line represents which velocity profile. We can even change the line display. We can add symbols for any lines. Apply. So we selected symbols for point D, so we can see that these are 10 points, and you can change it the Y direction from velocity to velocity in Y direction to velocity magnitude, and it should look like this. So there are so many options we can try and see the behavior of velocity and pressure and other parameters along the length and vice versa. And that's all for ANSYS CFX simulation for flow fast circular body.